1 server, then 5, then 5,000. What does a real load balancer setup actually look like at each tier? Today we find out. Welcome back, the final part of our load balancer deep dive. Today, the real world. Quick refresh. In part 2 we covered the 4 core algorithms: round robin, least connections, weighted, and IP hash. Plus health checks and sticky sessions. Now let's see how all this fits together in actual production systems. Tier 1, the small startup. NGINX running on a tiny $5 a month vPages S, in front of 2 application servers. NGINX is free, fast, rock solid. It handles a few thousand requests per second easily. For 90% of side projects and early-stage startups, this setup is more than enough. When you need more capacity, you don't redesign. You just add another backend server behind the same NGINX. Tier 2, mid-scale. You've outgrown the single vPages S. You move to AWS. The application load balancer in front. Behind it, an auto-scaling group of EC2 instances. The magic is auto-scaling. When traffic spikes, AWS automatically spins up new instances and adds them to the load balancer's pool. When traffic drops, instances are terminated. Tens of thousands of requests per second this way. The ALB itself is managed by AWS, so they handle the high availability of the load balancer too. Tier 3, Netflix scale, or anyone serving tens of millions of concurrent users. The architecture is hierarchical, multiple layers of load balancing. At the top, geographic DNS. When you watch Netflix from London, your DNS query is answered with the IP of the European data center, not the American one. This is geographic load balancing. Within each region, a regional load balancer routes traffic across availability zones. Inside each cluster, service-level load balancers. One for recommendations, one for video streaming, one for billing. Each layer scales independently. Each layer fails independently. The result is a system that can absorb tens of millions of concurrent streams and survive an entire data center going dark. Now, a problem. The load balancer hides all your servers behind one address. Great for users. But what happens when the load balancer itself fails? Every request stops being routed. Traffic has nowhere to go. Your entire system goes dark. Not because the servers failed. Because the door to the servers failed. This is what we call a single point of failure. SPOF. A single load balancer solves the server scaling problem by creating a worse one layer up. Solution 1. Active-passive failover. Run 2 load balancers. One handles all the traffic. The other sits quiet, watching. They heartbeat each other every second. If the active one stops responding, the passive takes over. Typically within a few seconds. Simple to understand, easy to set up. The downside? You're paying for 2 machines and one of them does nothing most of the time. Solution 2. Active-active. Both load balancers handle traffic at the same time. DNS returns both IP addresses, clients hit them in round robin. You're using both machines, getting double the capacity. If one dies, the other absorbs everything. The trade-off is complexity. Synchronizing state between 2 active load balancers is harder. Connections, sticky session mappings, health check results, all need to be shared or replicated. One more pattern: geographic load balancing. If your users are spread across the world, you don't want a user in Tokyo hitting a server in Virginia. The round-trip latency would be brutal. Geographic DNS solves this. The DNS answer depends on where the user is. London users get the European IP, Tokyo users get the Asia-Pacific IP. Inside each region, you still have all the other layers. Regional load balancer, service load balancer, auto-scaling. But the geographic layer keeps the request from crossing an ocean unnecessarily. When this comes up in a system design interview, expect probes like these. Probe 1. How would you handle a slow backend without removing it entirely? Answer: connection limits and circuit breakers. The load balancer caps connections per backend so a slow server doesn't drag everyone down. Probe 2. What happens if an entire region goes offline? Answer: geographic failover. DNSTTL is short, traffic reroutes to other regions. Latency increases but service stays up. Probe 3. When would you not use a load balancer? Answer: when you only have one backend, or you need strict ordering of requests, or when adding one creates more complexity than it solves. Probe 4. How does the load balancer itself stay highly available? Answer: active-passive or active-active setup, behind DNS or a virtual IP. That's the load balancer playlist. Part 1, the why and what. Part 2, how they decide. Part 3, real architectures and high availability. Next up in the System Design Fundamentals series, we tackle caching. Strategies, eviction policies, distributed caching, real-world failures. Subscribe so you don't miss it.